Okay, welcome to our PowerPoint. I've got some intro or some flying noises that happen here, so I apologize for those. We are starting Unit 4, and we'll be studying light and the atomic theory that is developed as our scientists were researching light. Way back in 1665, Isaac Newton, who's generally considered one of our first great physicists, was studying at Cambridge University in England. And on a sunny day, Newton made his room dark, made a little tiny hole in his window shutter, which allowed just a very narrow beam of light to enter the room. Then he took a glass prism, and here's the glass prism. The result was a spectacularly colored band that was the colors of the rainbow. And this is the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, that we now know is the electromagnetic spectrum range of visible light. And we'll talk about that in another slide. So these are the colors of the rainbow. This multicolored band is called a color spectrum because it is the whole range of light. There's coming some noise. Almost done. So Newton believed that all the colors he saw were in the sunlight that entered his room. So what he did was he first passed it through this first prism, and he got the rainbow. I'll just abbreviate that rainbow, the whole spectrum. Then passed it through a second prism. And if you will, it's not quite the correct term, reunited that light back into white light. So he just like inverted the direction of the prism. And he separated the white light. There's white light being fed in from the sun, separated into a rainbow, and then put it back into white light. Newton felt that light rays were made up of particles, so he subscribed to the particle theory of light. And nearly 150 years later, the person who we're going to look at first on our next slide found that diffraction was a property that light exhibited, and diffraction is a wave property. So let's go back again to say that Newton, where is my, okay, I can't find it. Sorry about that, I can't find how to separate that. Here's just another picture of Newton's experiment. Here's our white light. I like this one because it was in color. Here, of course, is our Roy G. Biv spectrum. And then you'll notice the different directions of the prisms, and then we're back to white light. Okay, next. So Fresnel discovered mathematically that the pattern of alternating light and dark lines, which we now call a diffraction pattern, produced light when it traveled through an aperture around an obstruction. We'll look at this later as a quick video, but if you look very carefully, you'll see that we have two slits. And then we have a concentric circle, and I don't know if I can erase, so I'm going to probably regret this. Our first circle is going like that, and here's where I want to get I want to find my colors. I can't find my other color. So there's that. So if I could do another color, my second wave is right here, and then they start running into each other. Where they run into each other, where waves run into each other, we get an interference pattern. And this is an interference pattern. Here's what an interference pattern looks like. An interference pattern is alternating dark light patterns. So this proved that light was a wave. This is the big thing here. The diffraction pattern Fresnel demonstrated is indicative of light exhibiting wave-like properties. Now, after that, 20 years later, Faraday in the 1830s demonstrated that if we put a magnetic field around a wire, we will get magnetic induction. So magnetic and electric, so that's leading us to something, electromagnetic. So what the heck does this all mean when we start going into this? And you will have, not in this slide, or not in this show, in this video, but we will have a lot more work that comes up even later where they started battling about whether light was a wave or a particle. After another 30 years had elapsed, we have another person named James Maxwell, and he developed a set of equations that confirm Faraday's idea that electricity and magnetism are two parts of a phenomenon called electromagnetism. So Maxwell showed that this electromagnetic phenomena would produce waves that traveled at the speed of light. Again, we'll have more information on the speed of light in upcoming lectures. Maxwell also suspected that there were light waves other than those that we can see, and he was right. So he gathered this whole range of electromagnetic radiation as electromagnetic spectrum, or EMS. That gives a big one. Which next class we will sing a song to celebrate the electromagnetic spectrum. So let's talk about waves. There are two main types of waves, and this is pretty easy, so take good notes here. Just pause if you need to. Transverse, and longitudinal. That link doesn't work. Lights move through space as two interacting transverse, make a note, light travels as two transverse disturbances. One is caused by the electric field and the other caused by the magnetic field. So there's two forces at play here. So the parts of the wave that you should be familiar with, and I've got that on our next slide. So let's go to our next slide and then come back. I'll come back to this part. Okay, please wait. It's not going to my next slide. There we go. So here is a transverse wave. Here is a longitudinal wave. And it's not a great image, but it's good enough. You will need to know, and you will be quizzed on all parts of the transverse wave. So here is a transverse wave. So you will need to know that the crest is this point on top, the trough is this point on the bottom. A wavelength is generally considered crest to crest, but it could also be trough to trough, either one. Amplitude is displacement from rest position. So the parts that you need to know are these parts that I will now make an arrow to: amplitude, wavelength, trough, and crest. Those parts. And notice that the transverse wave is the up-down displacement from parallel that we're used to seeing. We'll go back in a slide in a moment, but right now let's look at the longitudinal wave. also known as a compression wave. And that's like a compression and a rarefaction. So a rarefaction is where they're spread far apart, and a compression is when they're close together. And this kind of wave is a sound wave. Oh no, that's a sound wave. And I don't know if I'll be able to convey this on a video, but I'll talk about it when I get back. If you think of a transverse wave going up and down, and imagine that coming to your ear, like if you ear hit at a certain part, you wouldn't hear everything at a normal, constant level or frequency. But if the wave is coming after you in a pulse, then it's going to hit your ear, and the rarefactions and compressions will cause the movement of all the little parts in your ear that we need to have happen for hearing. So transverse waves is how light travels when consider its wave-like characteristics. Light does not travel in a longitudinal wave. And I'm going to go back now. So we did the parts of the wave. And another important factor or feature of wave motion is the inverse relationship. And here is an equation you will need to know. So C equals lambda, which is wavelength, and nu. I need to get another slide inserted here. I'm going to write this up here. C is speed of light, which we'll talk about in a few moments. Lambda is wavelength. And nu, which looks like a little V, is something we call frequency. Frequency. I'm sorry, I ran out of room. Let me write that. What about units, you ask? Well, the units are sort of a big deal on this. I'm going to go to this slide. Speed of light has a constant value of 3 times 10 to the 8th meters per second. Do you have to memorize this number? Absolutely not. This number is on your periodic table. So all you need to do is be able to look it up. Wavelength is measured in meters. Please notice the units of C are meters per second. So frequency is measured in cycles per second, which is abbreviated, weirdly enough, 1 over S, which is equal to S to the minus 1, which is equal to something we often write as Hz, which is pronounced hertz. And I'm sure this is going to run into this. Or 1 over S, or S to the minus 1. They're also known as the hertz. So let's look at this sample problem. And if class is almost over, you don't need to continue on this. So I think that you've probably done enough for today, but I will continue with this anyway. We're asked to calculate the frequency of light with a wavelength of 5.22 times 10 to the minus 10th meters. C equals lambda nu, and we're solving for frequency. So manipulating these 3 variables will give us V equals, and I'm going to write it like this. I don't even know what my backwards is. That's a C over lambda. So then remember, oh, I don't know C. You do too. You know that C is, I'm sorry about that, 3.00 times 10 to the 8th meters per second divided by our frequency, 5.22 times 10 to the minus 10th meters. If you've gotten this far in class, stop now, take your calculator out, and see if you get the number I'm about to show you. Notice that meters cross out, and we get 5.75 times 10 to the 17th per second. I hate that. I will do it like this, or preferably, I even like to go 5.75 times the 17th s to the minus 1. That's minus 1. And then I'm not going to do sample problem number 2 right now, because as I'm making this, it is time for me to get ready for my next class. Have a great rest of the day.